The universe contains star clusters older than almost everything else you can observe. They've been orbiting galaxies since before our solar system even existed. Most astronomers once thought all stars in a galaxy formed around the same time. They were fundamentally wrong. Some stellar neighborhoods assembled billions of years earlier than the rest. Tonight we're examining what makes these ancient clusters different from everything around them. We'll trace the evidence that reveals their extreme age, and we'll discover why their survival challenges our understanding of cosmic destruction. Before we dive into these timeless stellar cities, drop a comment about what sky objects fascinate you most. If you enjoy these cosmic explorations, consider subscribing. These journeys through space and time are meant to be shared. Stars usually spread out comfortably across space. Our sun sits far from its nearest neighbor. Collisions between stars remain impossibly rare in normal stellar neighborhoods. Some star clusters violate every expectation. Astronomers discovered fuzzy patches in telescopes centuries ago. When modern instruments finally resolved these patches, the truth emerged. Each one contained hundreds of thousands of stars packed into nearly perfect spherical formations. Scientists call these structures globular clusters, basically dense spherical star swarms. The geometry alone defies logic. Spiral arms make sense. Scattered distributions make sense. Perfect spheres containing 500,000 stars shouldn't happen naturally. Yet gravity makes it possible. Every star pulls on every other star with equal precision. No preferred direction exists. The only stable shape satisfying all those competing gravitational demands is a perfect sphere. At the cluster's core, stars pack so tightly that neighbors sit 1,000 times closer than our sun's nearest companion. These stellar cities represent gravitational architecture in its purest form. Most visible stars formed relatively recently in cosmic terms. Our sun qualifies as middle-aged. Many bright stars you observe are even younger. They represent the universe's latest stellar generations. These dense spherical clusters tell a completely different story. Their stars witnessed the universe's childhood. Astronomers read stellar ages by examining chemistry. Heavy elements like iron come from dying stars. Multiple stellar generations gradually contaminate galactic gas with these elements. Newer stars incorporate more heavy elements. Older stars contain almost none. Stars in these ancient clusters carry iron levels barely reaching 1% of our sun's content. That chemical poverty reveals extreme age. Measurements place these clusters at 13 billion years old. The universe itself is only slightly older at about 13.8 billion years. These stellar cities assembled when the cosmos had barely begun. Less than 1 billion years after the Big Bang. They preserve conditions from an era that newer stars can never authentically recreate. These aren't just old stars. They're cosmic fossils. These ancient spherical clusters maintain stability through pure physics. Gravity holds hundreds of thousands of stars in precise balance. Scientists developed mathematical models to understand this architecture. The density follows a specific pattern. Star concentration peaks at the center and gradually decreases outward. This isn't random distribution. Every star orbits within the cluster's gravitational field following mathematical laws. Astronomers measure how fast stars move randomly in different directions. This velocity tells us the gravitational well's depth. The measurements reveal something extraordinary. These structures have maintained their shape for billions of years through self-gravity alone. No external support exists. The balance comes from energy equilibrium. Gravitational energy pulling inward exactly matches the kinetic energy of stellar motion pushing outward. This balance creates what scientists call a self-gravitating system, structure held together purely by its own gravity. Without this perfect equilibrium, these clusters would either collapse inward or fly apart. Instead, they've survived since the universe's infancy. Every star in these ancient clusters should look old. Heavy stars burn fuel quickly and die young. After 13 billion years, only lightweight stars should remain alive. The heaviest survivors should be similar to our Sun. Telescopes reveal stars that shouldn't exist. Some cluster members appear hot and blue. Characteristics of young massive stars. Scientists call them blue stragglers because they straggle behind the normal aging process. Their existence defies stellar evolution. These stars didn't form recently, something rejuvenated them. Two scenarios explain this mystery. Binary stars can merge, combining their mass into a single heavier star that looks young. Or one star can steal material from a companion, gaining fresh fuel that reignites its surface. Both processes happen in these dense clusters. Stars pass close enough to interact gravitationally. Some capture companions. Others collide directly. The cluster's extreme density makes these encounters possible. Blue stragglers prove that stellar evolution in crowded environments follows different rules than isolated stars. These apparent youngsters reveal the violent stellar interactions happening within ancient spherical cities. Stars in these clusters don't stay where they formed. Gravity constantly reshuffles the population through a process taking billions of years. When stars pass close to each other, they exchange energy through gravitational interactions. Heavy stars tend to lose energy in these encounters. Light stars tend to gain energy. This energy exchange happens gradually through countless stellar encounters. The result transforms the cluster's structure. Heavy stars slowly sink toward the center as they lose energy. Light stars slowly drift toward the outer regions as they gain energy. Scientists call this mass segregation, the gravitational sorting of stars by weight. The process takes enormous time. Over billions of years, the cluster's center becomes dominated by heavy stars while lighter stars populate the outskirts. This isn't a quick reorganization. It's a glacial transformation that continues throughout the cluster's lifetime. Eventually, this segregation can destabilize the cluster's core. The central region becomes so dense that stars interact violently. Some escape the cluster entirely. Others form tight binary systems. Mass segregation reveals how these ancient structures continue evolving despite their extreme age. These dense stellar cities harbor objects found almost nowhere else. The extreme crowding creates conditions for bizarre stellar interactions. Dead stars called neutron stars form when massive stars explode. In normal space, neutron stars spin alone quietly. In these clusters, neutron stars capture companions and transform into something different. They steal gas from nearby stars and spin faster. Some reach rotation speeds of hundreds of times per second. Astronomers call these millisecond pulsars, basically recycled neutron stars spinning at absurd speeds. They emit beams of radiation that sweep across space like cosmic lighthouses. Multiple pulsars can exist in a single cluster. X-ray telescopes reveal even stranger objects. Some binary systems contain a neutron star or black hole actively feeding on a companion star. This produces intense X-ray emission. Other systems contain unusual pairs, a white dwarf orbiting a normal star in configurations rarely seen elsewhere. The cluster's dense core acts as a stellar laboratory. Random close encounters create binary systems that couldn't form in normal space. Some stars collide directly and merge. Others capture companions through gravitational interactions. These exotic objects reveal what happens when stellar evolution occurs in extreme density. These ancient structures survived billions of years, but they can't survive forever. Galaxy gravity slowly tears them apart through tidal forces. Clusters orbit through their parent galaxy. When they pass close to the galactic center, tidal forces intensify. Gravity pulls harder on the cluster's near side than its far side. This differential force stretches the cluster. Stars on the cluster's outer edge feel this tidal stress most strongly. Some gain enough energy to escape the cluster's gravity entirely. They leave behind tidal tails, long streams of escaped stars trailing the cluster's orbit. Each galactic passage strips away more members. The cluster loses mass gradually but inevitably. Smaller clusters disappear first. Larger ones survive longer but still shrink over time. Astronomers observe this destruction happening now. Some clusters show clear tidal tails extending across space. Others appear distorted, stretched by recent close passes near the galactic center. These ancient cities are dying. Not through violent catastrophe, but through slow gravitational erosion. The same tidal forces that destroy them also prove these clusters are genuinely ancient. Only structures billions of years old could show such advanced tidal damage. Not all these ancient clusters share identical chemistry. Some contain slightly more heavy elements than others. This diversity reveals a surprising history. Astronomers measure iron content in cluster stars. Most contain extremely low iron levels, barely 1% of our Sun's content. But some clusters show higher metallicity, reaching several percent of solar values. This chemical difference indicates different formation environments. Lower metallicity clusters formed first, from nearly pure hydrogen and helium. Higher metallicity clusters formed slightly later, after the first generation of stars had already polluted space with heavy elements. The diversity suggests multiple formation episodes. Some clusters assembled in the main galaxy. Others formed in smaller satellite galaxies that later merged with the main galaxy. When galaxies collide and merge, they bring their star clusters along. Our galaxy consumed multiple smaller galaxies throughout its history. Those devoured galaxies contributed their ancient clusters to our current collection. Chemical analysis reveals which clusters are native and which are immigrants. These stellar cities preserve evidence of ancient galactic cannibalism. Their chemistry tells the story of galaxy assembly across cosmic time. The densest cluster cores might hide something unexpected. Some clusters show velocity patterns suggesting a massive central object. Stars near a cluster's center should move randomly in all directions. Measurements sometimes reveal systematic patterns instead. Stars orbit faster than the cluster's visible mass should produce. This velocity anomaly suggests hidden mass. One explanation involves intermediate mass black holes. Objects heavier than stellar black holes but lighter than the supermassive monsters in galaxy centers. These intermediate black holes weigh thousands to tens of thousands of solar masses. In dense cluster cores, stellar collisions could build such black holes over time. A heavy star collapses into a stellar black hole. That black hole captures companions and swallows them. Through repeated mergers, it grows into an intermediate mass monster. Not all clusters necessarily harbor central black holes. The evidence remains debated. But the possibility reveals another way these ancient cities differ from normal stellar populations. Their extreme density and age provide conditions for building massive black holes through mechanisms impossible in ordinary space. If confirmed, these hidden monsters would represent another exotic product of life in ancient stellar cities. These ancient clusters don't sit still. They orbit through their parent galaxy on paths shaped by billions of years of gravitational history. Astronomers map cluster orbits by measuring positions and velocities. Some clusters follow nearly circular paths around the galactic center. Others follow highly elliptical orbits that carry them far from the galaxy and back again. Orbital shape reveals formation history. Clusters born in the main galaxy tend toward circular orbits. Clusters captured from satellite galaxies often show eccentric elongated orbits. They retain the orbital energy from their original galaxy's motion. Multiple cluster populations emerge from orbital analysis. One group formed in place. Another group arrived from accreted satellite galaxies. Their orbits preserve evidence of ancient galaxy mergers that assembled our current galaxy. Scientists can trace which satellite galaxy contributed which clusters by matching orbital families. This orbital archaeology reveals how our galaxy grew through consuming smaller neighbors. The clusters act as fossil records. Their positions and motions today tell us about galactic structure billions of years ago. These ancient stellar cities don't just preserve stellar evolution history. They preserve the entire galaxy's assembly history. These clusters survived 13 billion years, but that survival can't continue indefinitely. Astronomers can predict their ultimate fate. Two processes gradually destroy clusters. Tidal stripping removes outer stars during galactic passages. Internal evaporation ejects stars through gravitational interactions. Both processes continue relentlessly. The timeline varies by cluster mass. Small clusters will dissolve first, disappearing completely within several billion years. Massive clusters can survive much longer, potentially outlasting our sun's lifetime. But eventually all face the same fate. Stars escape one by one until the cluster's mass drops below a critical threshold. At that point, the remaining stars can no longer hold together gravitationally. The cluster evaporates completely. Some stars might fall into the galactic center. Others might escape into intergalactic space. A few might form tight binary systems that outlast the cluster itself. The cluster's constituent stars will survive as individuals, but the collective structure will vanish. These ancient cities represent some of the universe's oldest surviving structures. But survival isn't permanent. In the distant future, the last cluster will dissolve, erasing the final fossil record from the universe's childhood. Their eventual destruction makes their current existence even more precious. We're witnessing relics that won't exist forever. Every star burns fuel at a rate determined by its mass. Heavy stars consume their nuclear fuel rapidly. Light stars burn slowly and survive much longer. In these ancient clusters, the heaviest stars vanished billions of years ago. They exhausted their fuel and died when the universe was young. Their corpses remain as white dwarfs, basically dead stellar cores no longer producing energy. The surviving stars reveal the cluster's age through absence. Astronomers look at the most massive stars still burning normally. These stars sit at what scientists call the main sequence turn-off, the point where stars are just about to leave their stable burning phase. The turn-off mass tells us the cluster's age directly. Heavier turn-off stars indicate younger clusters. Lighter turn-off stars indicate older clusters. In these ancient spherical clusters, only stars lighter than our Sun remain on the main sequence. This pattern reveals ages exceeding 10 billion years. The missing heavyweights prove these clusters witnessed the universe's childhood. Stars don't die quietly when they exhaust core hydrogen. They transform into something far more dramatic before their final collapse. Medium-mass stars in these clusters have left the main sequence and entered a new phase. Their cores contract and heat up while their outer layers expand enormously. These bloated stars are called red giants. Massive evolved stars with cool surfaces glowing deep red. The transformation makes them incredibly luminous. A red giant can outshine hundreds of normal stars despite its cooler surface temperature. The size increase is staggering. If you placed one in our solar system, it would engulf multiple inner planets. These red giants dominate the cluster's visible brightness. They form a distinct branch on graphs plotting stellar brightness against temperature. Astronomers call this the red giant branch, basically the evolutionary track that aging stars follow. The branch's characteristics reveal the cluster's chemical composition and age. These brilliant red beacons represent the twilight phase of stellar life, a brief moment of glory before the final collapse into a white dwarf. After the red giant phase, some stars don't simply fade away. They ignite a new fuel source and stabilize temporarily. When a red giant's core becomes hot enough, helium fusion begins. This happens suddenly in a brief explosive event. The star then settles into stable helium burning. Scientists call these stars horizontal branch stars. They occupy a distinct horizontal region on brightness temperature diagrams. These helium-burning stars show remarkable color diversity. Some appear blue, others look yellow or red. This color spread depends on how much of their outer hydrogen envelope remains. Stars that retained more envelope appear redder. Stars that lost most of their envelope appear bluer. The horizontal branch reveals subtle differences between clusters. Some clusters show predominantly blue horizontal branches. Others show redder distributions. This diversity indicates slight variations in initial helium content or age. The horizontal branch serves as a cosmic laboratory. It demonstrates how stars can temporarily stabilize by burning a new fuel after exhausting their primary source. These stars represent a brief pause before the final descent into stellar death. Dead stars don't disappear. They linger as slowly cooling embers radiating leftover heat into space. When stars lighter than about 8 solar masses die, they shed their outer layers and leave behind their cores. These remnants are white dwarfs, basically exposed stellar cores no longer generating new energy through fusion. They simply radiate stored thermal energy gradually into space. The cooling process takes an immense time. A white dwarf starts extremely hot but cools predictably over billions of years. Scientists can measure a white dwarf's temperature and calculate how long it's been cooling. The coolest white dwarfs in these clusters provide independent age measurements. Their extreme faintness indicates billions of years of cooling. Some have temperatures barely above the cosmic background. Finding these ancient cooling embers requires powerful telescopes and patient observation. The white dwarf cooling sequence confirms ages derived from main sequence turn-off measurements. Both methods converge on similar numbers, around 13 billion years. These dead stars preserve thermal records from the cluster's formation. Their temperatures tell us precisely when the cluster assembled. Some horizontal branch stars don't shine steadily. They pulse rhythmically, brightening and dimming with clockwork precision. These pulsating stars are called Lyrae variables, basically horizontal branch stars that oscillate in brightness due to internal instabilities. The pulsation happens because the star's outer layers repeatedly compress and expand. Each cycle takes hours to complete. The pulsation period relates directly to the star's intrinsic brightness. Scientists can measure the period and calculate the star's true luminosity. Comparing true luminosity to apparent brightness reveals distance. This makes Lyrae variables incredibly useful as distance indicators. Dozens of these pulsating stars can exist in a single cluster. They all follow the same period-luminosity relationship. Their collective behavior provides precise distance measurements. These distances help calibrate the cosmic distance scale. The pulsation periods also reveal cluster properties. Period distributions indicate metallicity and age. Lyrae variables serve multiple roles: distance markers, age indicators, and metallicity probes. These cosmic metronomes demonstrate how stellar instability can become a powerful astronomical tool. Stars don't maintain their original chemistry unchanged. Nuclear processes and internal mixing gradually alter their surface composition. Lithium represents one of the lightest elements created shortly after the Big Bang. Stars contain small amounts of lithium in their outer layers initially, but lithium burns at relatively low temperatures compared to hydrogen. As stars age, convection zones carry surface material deeper into the stellar interior. When lithium reaches regions hot enough, it is destroyed through nuclear reactions. The star's surface lithium content drops over time as mixing continues. Measuring surface lithium abundance reveals stellar age. Younger stars retain more lithium. Older stars show severe lithium depletion. Stars in these ancient clusters contain almost no detectable lithium. Their atmospheres have been scrubbed clean through billions of years of internal mixing. The lithium depletion pattern matches predictions from stellar evolution models. It provides another independent age indicator confirming extreme antiquity. These stars have processed their outer layers so thoroughly that primordial lithium has essentially vanished. The missing lithium tells us these stars have been mixing their interiors for more than 10 billion years. The universe didn't start with the full periodic table. The Big Bang created only hydrogen, helium, and traces of lithium. Everything else came later. Heavy elements form inside massive stars through nuclear fusion. When these stars explode as supernovae, they scatter newly formed elements into space. Subsequent stellar generations incorporate these elements. Each generation contains slightly more heavy elements than the previous one. Astronomers use the term metallicity to describe heavy element content. Basically, anything heavier than helium counts as a metal in astronomical terminology. Our Sun has relatively high metallicity because it formed from gas enriched by many previous stellar generations. Stars in these ancient clusters show extreme metal poverty. Their iron content reaches barely 1% of the Sun's value. Some contain even less. This chemical signature proves they formed from nearly pristine gas before significant stellar enrichment occurred. The metal poverty is consistent across all cluster members. They all formed from the same primitive gas cloud. This uniformity confirms these clusters assembled in a single burst rather than gradually over time. The primitive chemistry directly reflects conditions in the early universe when heavy elements were extremely scarce. Nuclear fusion in the early universe didn't just create elements. It created specific isotopes in precise ratios that depended on cosmic conditions. During the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear reactions. This primordial nucleosynthesis created hydrogen, helium, and small amounts of lithium and beryllium. The relative abundances of different isotopes depended on conditions like density and expansion rate. Stars in these ancient clusters preserve part of that primordial chemical record, though stellar processing can modify some isotope signatures. Scientists compare light element ratios linked to ancient stars, such as helium-3 to helium-4, with predictions from primordial nucleosynthesis. These measurements constrain cosmological models. The observed ratios must broadly match predictions from Big Bang nucleosynthesis calculations. Major discrepancies would indicate problems with our understanding of the early universe. The isotope evidence connected to ancient cluster populations matches theoretical predictions remarkably well. It confirms the Big Bang model's basic framework. These stars serve as fossils not just of stellar evolution but of cosmic evolution. Their chemistry tells us about the universe's first moments. The transition from red giant to horizontal branch doesn't always happen smoothly. For some stars, helium ignition occurs catastrophically. When a red giant's core finally reaches helium fusion temperature, conditions can be extreme. The core has become degenerate. Basically, matter compressed so tightly that quantum physics dominates its behavior. In degenerate matter, temperature and pressure become partially decoupled. When helium ignites in a degenerate core, the fusion rate can explode suddenly. This helium flash releases enormous energy in seconds. The core temperature spikes dramatically before expanding and returning to normal density. The helium flash represents one of stellar evolution's most violent internal events. Despite the core explosion, the star's outer layers barely react. The energy release stays confined to the core region. An external observer would notice only subtle brightening. Stars experiencing helium flash transition directly to horizontal branch burning afterward. The flash marks the boundary between red giant and helium burning phases. Understanding this process required sophisticated computer models. These models demonstrate how quantum mechanics and nuclear physics combine to create explosive stellar transitions invisible from outside. Plot every star in a cluster by temperature and brightness. The resulting pattern tells you the cluster's complete life story. This graph is called a color magnitude diagram, basically a map showing where different evolutionary stages appear. Main sequence stars form a diagonal band. Red giants create a bright vertical branch. Horizontal branch stars occupy their namesake horizontal region. White dwarfs cluster in the faint corner. Each cluster shows the same basic pattern but with variations. The main sequence turn-off point shifts depending on age. The horizontal branch morphology changes with metallicity and helium content. The red giant branch's slope relates to chemical composition. Scientists compare observed diagrams with theoretical predictions from stellar evolution models. Agreement between observation and theory validates our understanding of how stars age. Discrepancies reveal gaps in the models requiring refinement. These ancient clusters provide the clearest color magnitude diagrams because all members have the same age and composition. They represent controlled experiments where only one variable changes: stellar mass. This makes them ideal laboratories for testing stellar evolution theory. The diagrams prove that we understand fundamental stellar physics correctly. These ancient clusters contain hundreds of thousands of stars at every evolutionary stage. They represent the ultimate test of stellar physics. Scientists build computer models predicting how stars should evolve based on fundamental physics: nuclear reaction rates, opacity calculations, equation of state, and energy transport. These models make specific predictions about stellar lifetimes, luminosities, and surface temperatures. The clusters allow direct comparison between prediction and reality. Every star provides a test case. The main sequence, red giant branch, horizontal branch, and white dwarf sequence must all match theoretical predictions simultaneously. The agreement is remarkable. Models accurately reproduce observed features in extreme detail. The main sequence turn-off occurs exactly where predicted. The red giant branch shows the expected slope and brightness. The horizontal branch morphology matches calculated distributions. This validation extends beyond simple existence confirmation. The models correctly predict subtle effects like lithium depletion rates, isotope evidence, and pulsation periods. These successes demonstrate that stellar evolution theory rests on solid physical foundations. Ancient globular clusters serve as cosmic laboratories where theory faces the most stringent observational tests. Their stars prove we genuinely understand how stars live and die. How do you predict where stars will be in a system with hundreds of thousands of members? Gravity provides the answer through pure mathematics. Astronomers developed models describing how star density changes from a cluster's center to its edge. The pattern isn't random. Stars concentrate most heavily at the core. Density gradually decreases, moving outward. The fall-off follows a specific mathematical curve. Scientists call this the King model, basically a mathematical description of how gravitational attraction creates predictable density patterns. The model assumes stars move randomly while gravity holds the system together. It predicts how many stars should occupy each region. Observations match predictions remarkably well. Telescope surveys counting stars at different distances from cluster centers reveal density profiles matching theoretical curves. The center contains the highest concentration. The outskirts show sparse distributions. The transition follows the mathematical pattern closely. This agreement shows that gravity sculpts cluster architecture. No other support is required. Stars simply respond to the collective gravitational field created by all members. The resulting structure represents pure gravitational mathematics made visible in space. These ancient structures should either collapse inward under gravity or fly apart from internal motion. They don't. A precise energy balance maintains stability. Gravity pulls all stars toward the cluster center. This creates gravitational potential energy, basically stored energy from the cluster's mass distribution. Stellar motion creates kinetic energy, the energy of stars moving through space. The two energies balance in a specific way. This relationship is called the virial theorem, a fundamental physics principle stating that stable self-gravitating systems maintain a specific ratio between potential and kinetic energy. The kinetic energy equals half the gravitational energy's magnitude. If stars moved too fast, kinetic energy would exceed the balance point. The cluster would expand or dissolve. If stars moved too slowly, gravitational energy would dominate. The cluster would contract catastrophically. The observed balance keeps both tendencies in check. This equilibrium persists for billions of years. Small disturbances trigger responses that restore balance. The virial theorem explains why these clusters maintain stable structures despite having no rigid framework. Pure energy balance provides the stability that keeps hundreds of thousands of stars bound together across cosmic time. Not all parts of a cluster behave identically. The innermost region shows distinct properties that characterize the entire structure. The core represents the central high-density zone where star concentration peaks. Scientists define core radius as the distance from center where density drops to half the central value. This measurement captures the cluster's most distinctive feature. Core sizes vary dramatically between clusters. Some show compact cores barely a few light-years across. Others display extended cores spanning dozens of light-years. This variation reflects different formation histories and evolutionary states. The core dominates the cluster's gravitational field. Stars near the core experience the strongest gravity and move fastest. This region controls how the entire cluster evolves over time. Core properties determine relaxation rates, mass segregation timescales, and eventual fate. Measuring core radius requires careful observation. Astronomers must count stars at multiple distances and fit the density profile. The core radius emerges as the natural length scale characterizing the structure. This single measurement tells you whether you're looking at a compact, dense cluster or a more diffuse, extended one. These clusters don't exist in isolation. They orbit within galaxies whose gravity competes with the cluster's own gravitational pull. Galaxy tidal forces stretch the cluster. Gravity pulls harder on the cluster's near side than its far side. This differential force creates tidal stress that tries to tear the cluster apart. The tidal radius marks where cluster gravity can no longer hold stars against galactic tidal forces. Beyond this boundary, stars escape into the galactic halo. The tidal radius defines the cluster's effective size, its sphere of gravitational influence. Tidal radius depends on both cluster mass and orbital distance from the galaxy center. Massive clusters maintain larger tidal radii. Clusters orbiting near the galactic center experience stronger tides and smaller tidal radii. The radius shrinks if the cluster loses mass through evaporation. Stars wandering beyond the tidal radius don't return. They become galactic field stars. Over billions of years, tidal stripping removes outer members and slowly reduces cluster mass. The tidal radius represents the battleground where cluster gravity confronts galactic gravity, the boundary determining which stars remain bound and which escape. Point a telescope at a cluster and measure brightness across its face. The pattern reveals fundamental structure. The center glows brightest. Moving outward, brightness decreases steadily. This isn't because central stars are individually brighter. It's because more stars occupy each square degree of sky near the center. The brightness follows a mathematical law. Surface brightness drops with distance from center in a predictable way. This relationship emerges directly from the density distribution. Astronomers plot surface brightness against radius to map cluster structure. The resulting curve shows how light concentrates toward the core. Deviations from the expected pattern indicate unusual features. Perhaps a central black hole or tidal disruption. The surface brightness profile provides a quick visual assessment of cluster properties. Compact clusters show steep brightness gradients. Extended clusters display gentler slopes. This simple measurement captures the essence of cluster architecture. How gravity organizes hundreds of thousands of stars into structures where light concentration reflects mass concentration. Stars in these clusters don't orbit in organized paths. They move randomly in all directions like molecules in a gas. Scientists measure how fast stars move in different directions. This spread of velocities is called velocity dispersion. Basically, the range of speed stars exhibit as they orbit through the cluster's gravitational field. Higher velocity dispersion indicates deeper gravitational wells. Stars must move faster to avoid falling inward when gravity pulls harder. Measuring velocity dispersion reveals the cluster's total mass. The relationship is straightforward. Square the typical velocity, multiply by the cluster's size. The result gives the mass. This technique works because the virial theorem connects velocity to gravitational potential. Velocity dispersion increases toward the cluster center. Central stars feel stronger gravity and move faster. Outer stars experience weaker gravity and move more slowly. Mapping this velocity gradient confirms that mass concentrates toward the core. These random stellar motions provide a gravitational scale. Faster motions mean more mass pulling everything inward. Stars in these clusters constantly exchange energy through gravitational encounters. This process erases memory of initial conditions. When two stars pass close together, their gravitational interaction transfers energy between them. One star gains speed, the other slows down. Over many encounters, stars gradually exchange energy until velocities follow a characteristic distribution. The relaxation time measures how long this equilibration takes. It depends on cluster density and stellar mass. Dense clusters relax faster because encounters happen more frequently. The timescale ranges from hundreds of millions to billions of years. After several relaxation times, clusters forget their initial velocity distribution. All memory of formation conditions vanishes. Stars achieve what physicists call a relaxed state, basically a configuration where energy distributes according to statistical laws rather than initial conditions. Young clusters haven't fully relaxed yet. Old clusters have relaxed multiple times. These ancient globular clusters show fully relaxed structures. Their velocity distributions match theoretical predictions closely. The relaxation process demonstrates how gravitational interactions transform chaotic initial conditions into ordered statistical patterns over cosmic time. Every gravitational well has a threshold. Move fast enough and you escape permanently. Escape velocity represents the minimum speed needed to leave a cluster's gravitational influence forever. Reach this speed and you'll coast outward indefinitely without falling back. Move slower and gravity eventually pulls you back toward the center. The escape velocity depends on position. Near the center where gravity is strongest, escape velocity is highest. At the tidal radius where cluster gravity weakens, escape velocity drops to nearly zero. Stars at the edge require minimal speed to escape. Scientists calculate escape velocity from cluster mass and radius. The relationship is simple. More massive clusters have higher escape velocities. Smaller clusters show lower thresholds. Stars occasionally reach escape velocity through gravitational encounters. A close pass with another star can accelerate one member beyond the escape threshold. That star departs the cluster permanently. This evaporation process slowly erodes cluster mass over billions of years. Escape velocity defines the boundary between bound members and future escapees. The speed threshold determining which stars remain trapped and which break free. Some clusters appear tightly concentrated. Others look diffuse and extended. Scientists quantify this difference. The concentration parameter compares core radius to tidal radius. Divide the tidal radius by core radius and take the logarithm. The result measures how centrally concentrated the structure is. High concentration means small core and large overall size. These clusters show extreme density contrasts between center and edge. Low concentration indicates more uniform density distribution. Concentration correlates with evolutionary state. Clusters that have undergone core collapse show very high concentration. Young relaxed clusters typically show moderate values. The parameter captures in one number what takes paragraphs to describe. Astronomers classify clusters by concentration. This single measurement predicts many other properties. Highly concentrated clusters evolve faster, lose stars more readily, and face different fates than diffuse ones. The concentration parameter demonstrates how simple ratios can characterize complex structures. One number reveals whether gravity has compressed the core into extreme density or spread mass more evenly. Hundreds of thousands of stars orbit through these clusters. None follow simple elliptical paths. Yet the system remains stable. Each star responds to the combined gravitational pull of all other members. This creates a smoothly varying gravitational field. Stars orbit within this field following complex paths that constantly change direction. Despite this complexity, the system remains in balance. Scientists call this dynamical equilibrium. Basically the condition where inward gravitational pull and stellar motion balance across the system. This equilibrium allows stable orbits, despite lacking a central massive object. Unlike planetary systems where one star dominates, cluster members all contribute comparably to the gravitational field. Each star orbits the collective potential rather than any individual body. The equilibrium persists because the system adjusts automatically. If a region becomes too dense, stars there move faster and spread out. If a region thins, stars there slow down and cluster together. These self-regulating responses maintain stability. Dynamical equilibrium proves that hundreds of thousands of stars can orbit together indefinitely through collective gravitational organization rather than central dominance. These clusters need no external support. They exist as isolated gravitational systems bound by their own mass. Unlike gas clouds supported by pressure or star systems confined by galactic tides, globular clusters bind through self-gravity alone. The cluster's own mass creates the gravitational field holding it together. Remove the cluster from the galaxy and it remains stable. This makes them fundamentally different from galactic structures. Spiral arms require galactic rotation to maintain. Star-forming regions need external compression. Globular clusters require nothing beyond their constituent star's mass. Self-gravitating systems follow universal physical laws. The virial theorem governs their equilibrium. Relaxation processes determine their evolution. These principles apply to any collection of particles interacting gravitationally, from star clusters to galaxies to dark matter halos. The mathematical simplicity of self-gravitating systems makes them ideal physics laboratories. They demonstrate gravitational dynamics in pure form without complications from gas, magnetic fields, or external forces. These ancient spherical clusters represent gravity's handiwork. Stable structures maintained by nothing more than mutual attraction between hundreds of thousands of stars across billions of years. Ancient clusters contain a puzzle that defied explanation for decades. All member stars should look old. Heavy stars died billions of years ago. Only lightweight survivors should remain burning their fuel slowly. Telescopes reveal stars that violate this expectation. Some cluster members appear hot and blue. These characteristics indicate youth. Young, massive stars burn hotter and bluer than old, lightweight ones. The contradiction seems impossible. These clusters formed 13 billion years ago. No star massive enough to appear blue should survive that long. Heavy stars exhaust their fuel in millions of years, not billions. Yet these anomalous blue stars occupy positions on brightness temperature diagrams where only young stars should appear. Scientists call them blue stragglers, basically stars that straggle behind the normal aging process by appearing younger than they should be. They extend the main sequence upward into regions where ancient cluster members shouldn't exist. Their presence demands explanation. Something rejuvenated these stars or created them recently. Either scenario challenges our understanding of stellar evolution in isolated ancient systems. Blue stragglers represent one of globular cluster astronomy's most intriguing mysteries. Two separate stars can become one through catastrophic merger. This process creates stars that appear younger than their actual age. Many stars exist in binary pairs orbiting each other. As these pairs age, orbital evolution brings them closer together. Eventually, some binaries spiral inward until the stars touch. When contact occurs, the merger happens quickly on astronomical timescales. The combined mass creates a star heavier than either original component. This new merged star appears on the main sequence at a position determined by its total mass. That position looks identical to where a genuinely young massive star would appear. The merger resets the stellar clock. The new star's surface shows fresh hydrogen. Its core contains more fuel than either parent possessed individually. It burns brighter and hotter than an old star should. Binary mergers occur more frequently in dense cluster cores where close encounters are common. Gravitational interactions can shrink binary orbits or trigger instabilities leading to coalescence. The merger process demonstrates how stellar collisions can create objects that masquerade as young stars despite forming from ancient components. Stars in binary systems don't always remain isolated from their companions. Sometimes one star steals material from its partner in a process that reverses aging. Binary evolution brings stars into close proximity. When one star expands into a red giant, its outer layers can overflow onto its companion. This mass transfer process feeds fresh hydrogen onto the receiving star's surface. The recipient gains both mass and fuel. Its surface becomes rich with unburned hydrogen. The star grows hotter and more luminous. Despite its ancient core, the surface looks rejuvenated. The mass donor shrinks as it loses material. Eventually, it may strip down to its core. The recipient, meanwhile, appears progressively younger. It moves to positions on the main sequence occupied by more massive stars. This rejuvenation happens without merger. The two stars remain separate. One becomes a stripped core while the other masquerades as a young massive star. Mass transfer provides an alternative route to creating blue stragglers, recycling fuel between aging companions rather than combining them entirely. Some stellar systems contain 3 stars orbiting in complex configurations. These systems evolve very differently from simple binary pairs. Triple star systems exhibit chaotic dynamics. The 3 bodies interact gravitationally in ways that cannot be solved by simple equations. Orbits can flip, exchange partners, or eject members entirely. These complex interactions create unusual evolutionary pathways. One star might capture material from 2 companions. Orbital energy exchange might compress one binary while expanding another. The possibilities multiply compared to simple 2-body systems. Some triple systems produce blue stragglers through interactions impossible in binary pairs. The third star's gravitational influence can trigger mergers or enhance mass transfer. It can also stabilize configurations that would be unstable with only 2 stars. Triple systems are relatively common in dense cluster cores. Close encounters can cap third companions into existing binaries. The resulting 3-body dynamics transform ordinary stellar evolution into something far more complex. These systems demonstrate how gravitational chaos in crowded environments produces outcomes never seen in isolated binary evolution. In the densest cluster regions, stars don't just pass by each other. Sometimes they collide directly. Stellar collisions happen when 2 stars approach within touching distance. The encounter timescale becomes faster than the stars can respond. They merge violently in a head-on crash. The collision releases enormous energy. The stars' outer layers mix together. The cores combine. The resulting object settles into a new equilibrium as a single merged star with properties determined by the combined mass. These direct collisions occur preferentially in cluster cores where star density reaches extreme values. Collision rates depend on both density and stellar velocities. Higher density increases encounter frequency. Lower velocities increase collision probability during encounters. Collision products can appear as blue stragglers if the merged mass exceeds the cluster's main sequence turn-off mass. The crash literally creates a more massive star from less massive components. Direct stellar collisions represent the most violent route to producing rejuvenated-looking stars, cosmic car crashes that forge new stellar entities from the wreckage. Blue stragglers rotate faster than normal cluster members. This rapid rotation provides crucial clues about their formation. Most old stars rotate slowly. Stellar winds and magnetic braking reduce rotation over billions of years. Ancient cluster members should spin leisurely by now. Blue stragglers violate this expectation. Measurements reveal rotation speeds significantly exceeding those of normal turn-off stars. Some spin tens of times faster than comparable mass stars should. The rapid rotation indicates a violent formation history. Binary mergers conserve angular momentum from the original orbital motion. The merged product spins rapidly as orbital energy converts to rotation. Mass transfer can also spin up the receiving star through added angular momentum. Scientists measure rotation through stellar spectroscopy. Faster rotation broadens spectral lines in predictable ways. These measurements distinguish between different formation scenarios. Rapidly rotating blue stragglers likely formed through mergers or mass transfer. Slowly rotating ones might have different origins. Rotation speed serves as a fossil record revealing the violent encounters that created these puzzling objects. Blue stragglers don't distribute randomly throughout clusters. Their positions reveal where and how they formed. Some clusters show blue stragglers concentrated in the dense core. Others display blue stragglers scattered throughout. Still others exhibit both populations simultaneously. This bimodal distribution indicates multiple formation mechanisms. Core concentrated blue stragglers are likely formed through collisions or dynamical encounters possible only in high-density regions. Scattered blue stragglers probably formed through binary evolution processes that can happen anywhere. The spatial pattern changes with cluster properties. Denser clusters show more centrally concentrated blue stragglers. Less dense clusters display more uniform distributions. The core density determines which formation mechanism dominates. Mapping blue straggler positions tests theoretical predictions. Models predict where different formation channels should produce blue stragglers. Observations confirm these predictions. The spatial distribution demonstrates that environment controls formation mechanism. Violent collisions in dense cores versus gentler binary evolution in the outskirts. Blue stragglers look young but aren't. Their surface chemistry sometimes reveals the truth. Normal main sequence stars show consistent surface compositions matching their formation environment. Blue stragglers sometimes display subtle chemical anomalies that distinguish them from genuinely young stars. The anomalies depend on formation mechanism. Binary mergers might mix core processed material to the surface. Mass transfer can deposit chemically peculiar material from an evolved companion. Collisions can dredge up interior material through violent mixing. Spectroscopy reveals these differences. Detailed chemical analysis shows element ratios that don't match normal expectations. Some blue stragglers show enhanced helium or peculiar carbon to nitrogen ratios. Others display normal surface chemistry indistinguishable from standard main sequence stars. The chemical diversity indicates multiple formation pathways. Not all blue stragglers form identically. Some preserve chemical signatures of their violent origins. Others hide their past behind normal-looking surfaces. Surface composition provides another diagnostic separating different formation scenarios. Chemical fingerprints revealing how these mysterious stars acquired their deceptive youth. Some blue stragglers emit X-rays at levels far exceeding normal stars. This high-energy radiation reveals ongoing stellar interactions. as X-ray telescopes detect emission from hot gas surrounding certain blue stragglers. The temperatures required to produce X-rays exceed millions of degrees. Normal stellar atmospheres don't reach these extremes. The X-rays come from companion interactions. Some blue stragglers remain in binary systems even after mass transfer or merger. The companion might be a white dwarf or another compact object. Material flowing between the stars heats up and radiates X-rays. Other blue stragglers emit X-rays from magnetically active coronas. Rapid rotation from merger or mass transfer amplifies magnetic activity. The enhanced magnetic fields heat coronal gas to X-ray emitting temperatures. X-ray observations identify which blue stragglers have companions and which rotate rapidly. The emission provides real-time evidence of ongoing activity. These observations confirm that many blue stragglers didn't simply form and stop evolving. They continue interacting with companions or sustaining enhanced magnetic activity from their violent formation. X-rays reveal the continuing legacy of the collisions and mergers that created them. No single mechanism explains all blue stragglers. Multiple processes create them through different pathways. Scientists developed several competing models. Binary mergers predict one set of properties. Mass transfer predicts different characteristics. Direct collisions produce yet another signature. Each mechanism leaves distinct fingerprints. The models make testable predictions. Merger products should rotate rapidly and show certain chemical peculiarities. Mass transfer systems might retain companions and emit X-rays. Collision products should concentrate in dense cores. Observations confirm all mechanisms operate. Some blue stragglers match merger predictions. Others clearly formed through mass transfer. Still others show collision signatures. The cluster environment determines which mechanism dominates. Dense cores favor collisions and dynamical encounters. Less dense regions promote binary evolution. Some clusters produce blue stragglers through multiple channels simultaneously. The diversity of formation scenarios demonstrates that stellar evolution in crowded environments offers many routes to creating stars that appear younger than their actual age. Advanced telescopes finally provided evidence distinguishing between competing formation theories. The observations came from space-based instruments avoiding atmospheric distortion. The Hubble space telescope delivered unprecedented clarity. Its precise photometry measured stellar brightnesses and colors with accuracy impossible from ground-based observatories. These measurements revealed subtle differences between blue straggler populations. The observations showed rotation rates, binary frequencies, and spatial distributions all varying between clusters and between blue stragglers within individual clusters. No single formation mechanism could explain all the data. The evidence confirmed that multiple pathways produce blue stragglers. Collisions dominate in very dense cores. Binary evolution operates throughout clusters. Mass transfer creates some blue stragglers while mergers create others. The precision measurements transformed blue stragglers from puzzles into powerful diagnostic tools. Their properties now trace dynamical processes in cluster cores. Their distributions map density evolution over billions of years. What began as an impossible mystery became a window into stellar interactions in extreme environments. Proof that apparent contradictions often hide deeper truths about how nature operates. Stars passing near each other don't just continue unchanged. Every close encounter transfers energy through gravity. When two stars approach, their gravitational fields interact. The interaction deflects both trajectories. One star typically gains speed, the other loses speed. The total energy remains constant but redistributes between participants. The outcome depends on stellar mass. Heavy stars tend to lose energy in these encounters. Light stars tend to gain energy. This isn't random luck. Statistical mechanics dictates the pattern. Think of it like colliding balls of different weights. Heavy objects tend to slow down when encountering light ones. Light objects speed up after encounters with heavy ones. Stars behave similarly through gravitational interactions. These energy exchanges happen constantly in dense clusters. Every stellar passage redistributes energy slightly. Individual exchanges barely matter, but accumulate millions of encounters over billions of years, and the cumulative effect transforms the cluster's structure. Energy exchange represents the fundamental process driving long-term cluster evolution. Heavy stars don't remain where they formed. They slowly migrate inward over cosmic time. As heavy stars lose energy through gravitational encounters, their orbits shrink. Lower energy means tighter binding to the cluster's gravitational well. The stars sink toward regions of deeper potential, the cluster core. This migration happens imperceptibly. A single encounter changes orbital energy negligibly, but repeated encounters accumulate. Over hundreds of millions of years, heavy stars drift systematically inward. The process accelerates as stars approach the core. Encounter rates increase with density. More encounters mean faster energy loss. Heavy stars near the core sink even more rapidly than those in the outskirts. Eventually, the cluster core becomes dominated by its heaviest members. Main sequence stars more massive than average concentrate centrally. Stellar remnants like white dwarfs populate the inner regions preferentially. This central concentration demonstrates how gravity sorts stellar populations by weight over billions of years. While heavy stars sink inward, light stars move in the opposite direction. They slowly migrate toward the cluster's outer regions. Light stars gain energy through the same encounters that drain heavy stars. Higher energy means weaker binding to the cluster. These energized stars orbit through larger volumes, reaching farther from the core. The outward migration proceeds gradually. Each encounter provides a tiny energy boost. Accumulating countless boosts over time pushes light stars progressively outward. They populate increasingly distant regions as their orbital energy grows. Some light stars gain enough energy to reach the cluster's tidal radius. A few exceed escape velocity entirely. These escapees leave the cluster permanently. The majority remain bound but occupy the outermost regions. The cluster physically expands as light stars migrate outward. The overall size increases while the core contracts. This simultaneous core contraction and envelope expansion represents the signature of ongoing mass segregation. Gravity actively sorting stellar populations by driving heavy stars inward and light stars outward. Count the stars at different distances from a cluster's center. The mass distribution changes dramatically with location. The cluster core contains disproportionately many heavy stars. Main sequence stars near the turnoff mass dominate. White dwarfs concentrate here. The average stellar mass exceeds the cluster-wide average significantly. The outer regions show the opposite pattern. Light stars dominate. Low-mass red dwarfs become the primary population. White dwarfs and heavy main sequence stars are conspicuously rare. The average mass falls well below the cluster mean. Scientists call this the mass function. Basically, the distribution of stellar masses in different regions. Mass segregation transforms an initially uniform mass function into one that varies with location. Measuring the mass function tests dynamical evolution models. Theory predicts how mass distributions should evolve. Observations confirm these predictions. The radially dependent mass function proves that gravitational encounters have been sorting stars by weight for billions of years. Imagine hundreds of thousands of objects constantly exchanging energy through gravitational encounters. Eventually, they reach a predictable state. The relaxation process drives stellar velocities toward a specific distribution. Initially, stars might have any velocity pattern. Encounters gradually erase this initial configuration. After sufficient time, velocities follow what physicists call a Maxwell-Boltzmann distribution. Basically the same statistical pattern that gas molecules follow. The distribution doesn't mean all stars move at identical speeds. It means velocities spread according to predictable statistical laws. Heavy stars move slower on average, light stars move faster. The relationship follows thermal equilibrium principles. Relaxation erases all memory of initial conditions. After several relaxation times, the cluster forgets how stars were distributed originally. Only the current mass and structure matter. History becomes irrelevant. This statistical evolution demonstrates deep connections between stellar dynamics and thermodynamics. Stars behave like particles in a gas reaching thermal equilibrium. The relaxation process proves that gravitational systems follow universal statistical laws despite their apparent complexity. Density increases in contracting cores. You might expect temperatures to drop as stars spread their energy over smaller volumes. The opposite happens. As the core contracts under gravity, gravitational potential energy converts to kinetic energy. Stars move faster to maintain equilibrium in the deeper potential well. Faster motion means higher effective temperature. This gravitational heating creates a paradox. The system loses energy to the envelope, yet the core becomes hotter. The explanation lies in how self-gravitating systems respond to energy loss. Normal systems cool when they lose energy. Self-gravitating systems have negative heat capacity. Losing energy makes them hotter rather than cooler. This counterintuitive behavior drives continued core contraction. The heating accelerates mass segregation. Higher core temperatures mean faster stellar velocities. Faster velocities increase encounter rates. More encounters speed energy transfer. The core heats further and contracts more rapidly. Gravitational heating demonstrates how self-gravitating systems follow thermodynamics rules completely opposite to ordinary matter. Mass segregation doesn't continue forever at steady rates. It can trigger catastrophic instability. As heavy stars concentrate in the core, density increases. Higher density means more frequent encounters. More encounters accelerate energy transfer. Energy flows faster from core to envelope. The core contracts more rapidly. This creates positive feedback. Contraction increases density. Higher density speeds energy loss. Faster energy loss accelerates contraction. The cycle reinforces itself. Eventually, the core enters runaway collapse. Density skyrockets while the core radius plummets. The contraction accelerates until physical process is halted. Close binaries can absorb energy and stop the collapse. Direct collisions might halt it through energy injection. Not all clusters experience core collapse. Low-density clusters evolve too slowly. Tidal disruption might destroy them before collapse occurs. High-density clusters often show collapsed cores. Tiny central regions with extreme stellar densities. Core collapse represents the ultimate endpoint of mass segregation when gravitational instability overcomes all stabilizing mechanisms. While cores collapse, cluster envelopes don't remain static. They expand outward in response to energy flowing from the core. Energy lost by the core must go somewhere. It flows outward into the cluster envelope. Stars in outer regions gain this energy. Higher energy means larger orbits. The envelope grows. This expansion happens gradually but inexorably. The cluster's overall size increases even as its core shrinks. The half-mass radius, the radius containing half the cluster's mass, grows larger over time. The expansion rate depends on core evolution. Faster core contraction drives faster envelope expansion. Clusters approaching core collapse show accelerating envelope growth. The outer boundary pushes steadily outward. Eventually, expanding envelopes encounter tidal limits. Stars reaching the tidal radius escape. The cluster loses mass through evaporation. Envelope expansion coupled with tidal stripping slowly erodes cluster mass. This simultaneous core collapse and envelope expansion demonstrates how energy flows reshape the entire structure over billions of years. Mass segregation doesn't just rearrange stars, it drives some stars away completely. As light stars gain energy and migrate outward, some reach escape velocity. These stars depart permanently. The cluster's population decreases gradually through this evaporation process. Mass segregation accelerates evaporation. Light stars concentrate in outer regions near the tidal radius. They need less additional energy to escape. Encounters can easily push them over the threshold. The evaporation rate increases with advanced mass segregation. Young clusters evaporate slowly. Old segregated clusters lose stars rapidly. The rate depends on how thoroughly mass segregation has concentrated light stars near the escape boundary. This mass loss feeds back into cluster evolution. Losing stars reduces total mass. Lower mass means weaker gravitational binding. Remaining stars escape more easily. The cluster shrinks and evaporates ever faster. Mass segregation ultimately dooms clusters to dissolution by driving their lightest members toward escape while concentrating heavy stars in unstable dense cores. Mass segregation doesn't happen overnight. The process unfolds over cosmic time. The timescale depends on cluster properties. Dense clusters segregate faster because encounter rates are higher. Massive clusters take longer because more encounters are needed to redistribute energy throughout larger populations. Typical segregation timescales span billions of years. Some clusters show little segregation because they're too young. Others display complete segregation because they've evolved for 10 billion years. The degree of segregation indicates evolutionary age. Scientists calculate expected timescales from cluster properties. Comparing calculations to observations tests whether clusters have evolved as predicted. Good agreement confirms that mass segregation proceeds at rates determined by gravitational dynamics. The extended timescale means we're observing a process in progress. Mass segregation continues happening in clusters today. It started billions of years ago and will continue billions of years into the future. These ancient structures remain dynamically active despite their extreme age. Cluster mass predicts how quickly mass segregation proceeds. Astronomers discovered this relationship through systematic observations. Scientists examined many clusters measuring both total mass and segregation degree. A clear pattern emerged. More massive clusters show less advanced segregation for their age. Less massive clusters display more complete segregation. This correlation reflects fundamental physics. Relaxation time increases with cluster mass. More massive systems take longer to exchange energy throughout their populations. Segregation requires multiple relaxation times to complete. Astronomers often describe this as a mass relaxation correlation. It predicts segregation timescales from observable properties like mass and size. This empirical law allows age estimation from dynamical state. Measure a cluster's segregation degree in mass. Calculate how long segregation should take. Compare to the cluster's actual age. Discrepancies reveal unusual evolutionary histories. The mass timescale correlation proves that simple physics principles govern the complex evolution of systems containing hundreds of thousands of gravitationally interacting stars. X-ray telescopes pointed at these ancient clusters detected something unexpected. Intense X-ray emission poured from specific locations within the stellar swarms. The emission comes from binary star systems containing compact objects. A neutron star or black hole orbits a normal companion star. Material streams from the companion onto the compact object through gravitational attraction. This infalling material does not land gently. It spirals inward, forming an accretion disk, basically a rotating disk of gas gradually falling toward the compact object. Friction in the disk heats the gas to millions of degrees. At these extreme temperatures, the gas radiates X-rays. The X-ray brightness reveals the feeding rate. More material flowing inward produces stronger emission. Some systems shine so brightly in X-rays they outshine the entire cluster in visible light. These X-ray binaries form through dynamical encounters in dense cluster cores. A compact object captures a normal star through gravitational interaction. The resulting binary survives and evolves into an actively feeding system. Dense clusters can contain dozens of these X-ray sources. Their emission proves that dead stars can become remarkably luminous by cannibalizing companions. Some neutron stars spin hundreds of times per second. This seems impossible for objects that should have slowed down billions of years ago. Normal neutron stars form in supernova explosions. They initially spin rapidly but slow down over millions of years through magnetic braking. Ancient neutron stars in these clusters should barely rotate. Radio telescopes detected neutron stars spinning at absurd rates. Some complete rotations in just a few milliseconds. Scientists call them millisecond pulsars. Basically, neutron stars spinning fast, they emit radio pulses hundreds of times per second. The rapid rotation comes from recycling. These neutron stars once had companions. Material transferred from companion to neutron star carried angular momentum. This spin-up process accelerated the neutron star's rotation dramatically. The companion eventually disappeared. It either evaporated from mass loss or became a white dwarf too faint to detect. The neutron star remains, spinning at speeds impossible for isolated objects. Millisecond pulsars prove that stellar evolution can resurrect dead stars and transform them into exotic, rapidly rotating beacons through mass transfer. Some blue stragglers are not solitary objects. They have invisible companions revealed only through careful observation. Precise measurements show some blue stragglers wobble slightly in their positions. The wobble indicates an unseen companion pulling gravitationally. Spectra reveal this companion is a white dwarf, basically a dead stellar core. These systems form through binary evolution. One star evolved off the main sequence first and shed its envelope. The exposed core became a helium white dwarf. The companion received the transferred material and appeared rejuvenated. The result is a peculiar pairing. A seemingly young blue star orbits an extremely low-mass white dwarf. The white dwarf's low mass proves it never completed normal stellar evolution. It lost its envelope prematurely through mass transfer. Scientists call these systems blue stragglers with helium white dwarf companions. They represent a specific evolutionary pathway different from merger-produced blue stragglers. The companion's presence reveals the rejuvenation mechanism. These peculiar binaries demonstrate how mass transfer creates bizarre stellar pairs impossible in isolated evolution. Not all cluster members remain trapped. Some race through space at speeds far exceeding normal stellar velocities. Massive stars in these clusters exploded as supernova billions of years ago. The explosions left behind neutron stars or white dwarfs. Some of these remnants received violent kicks during the explosion process. The kicks can exceed the cluster's escape velocity. The remnant shoots away at high speed. These objects are called hypervelocity stars or runaway objects. Basically, stellar remnants ejected through violent birth processes. Astronomers detect these escapees through their motion. They trace trajectories back to cluster centers. The remnants originated in the cluster but now travel far from their birthplace. Some reach distances exceeding hundreds of light years. The ejection process reveals explosion asymmetries. Perfectly symmetric explosions would not produce kicks. The observed velocities indicate significant asymmetry during core collapse. Runaway remnants preserve evidence of violent deaths that occurred billions of years ago when massive cluster stars reached the ends of their lives. Some binary stars orbit so close they actually touch. Their surfaces merge into a shared envelope surrounding both cores. Normal binary stars maintain separation between their surfaces. Contact binaries violate this expectation. The two stars share a common outer layer. They orbit within their combined envelope. This configuration forms when binary orbits shrink through angular momentum loss. Magnetic braking or gravitational radiation removes orbital energy. The stars spiral inward until their surfaces meet. The merged envelope rotates as a single unit. Both cores orbit within this shared atmosphere. The system looks like a peanut-shaped single object from a distance. Only detailed observations reveal the dual-core nature. Contact binaries concentrate in cluster cores where binary formation rates are highest. They represent an intermediate stage between separated binaries and complete mergers. These systems demonstrate that binary evolution can create configurations where stellar identity blurs. Two stars orbiting within one shared envelope. These clusters contain unusually high numbers of stars that rhythmically change brightness. The concentration far exceeds normal stellar populations. Variable stars pulsate due to internal instabilities. Their outer layers alternately compress and expand. This pulsation creates periodic brightness changes detectable from Earth. Certain types of variables populate these clusters preferentially. RR stars, basically horizontal branch pulsators, appear in large numbers. Some clusters contain dozens. Type 2 Cepheids and SX Furnaces variables also concentrate here. The high concentration reflects stellar evolution stage. These variable types occupy specific positions on evolutionary tracks. Ancient cluster populations have evolved into stages where pulsation instability occurs frequently. The variables serve multiple purposes. They indicate distances through period luminosity relations. They reveal cluster ages through pulsation properties. They demonstrate stellar evolution through their abundances. The variable star enrichment proves that old stellar populations naturally concentrate pulsating stars at specific evolutionary phases. Planetary nebulae are rare in these ancient clusters. When they appear, they reveal stellar death in progress. A planetary nebula forms when a red giant sheds its outer layers. The exposed core becomes a white dwarf. Ultraviolet radiation from the hot core ionizes the surrounding ejected gas. The gas glows, creating a visible nebula. These nebulae appear rarely in clusters because they fade quickly. The glowing phase lasts only tens of thousands of years. In a cluster containing hundreds of thousands of stars, only a few might display visible nebulae at any given time. Telescopes have detected several planetary nebulae within globular clusters. They appear as small glowing shells around faint central stars. The nebula confirm that stellar mass loss happens even in low metallicity environments. The rarity makes each detection valuable. Scientists can study planetary nebula formation in pristine chemical environments. The nebula preserve records of late stellar evolution in conditions matching the early universe. These rare glowing shells demonstrate that even ancient metal-poor stars create beautiful death shrouds when they shed their outer layers. Not all evolved stars show normal chemical compositions. Some display bizarre element patterns impossible in standard evolution. Certain red giants in these clusters show enhanced carbon or barium abundances. Their spectra reveal element ratios that should not exist in such old stars. Scientists call them chemically peculiar giants, basically evolved stars with anomalous surface compositions. The peculiarities come from binary mass transfer. A companion star evolved first and produced unusual elements through internal nuclear processes. It transferred this processed material onto the current giant surface before dying. The companion now exists as a white dwarf too faint to detect easily. The giant's surface preserves the chemical signature of its dead companion's interior. The anomalous abundances reveal past interactions invisible through current observations. These chemically peculiar stars concentrate in globular clusters because binary interactions are common in dense environments. They demonstrate that stellar surfaces do not always reflect simple evolution. Some stars carry chemical fingerprints inherited from dead companions, living records of extinct stellar interiors. Most white dwarfs show weak or undetectable magnetic fields. Some cluster white dwarfs violate this pattern dramatically. Spectroscopic observations reveal white dwarf with field strengths reaching millions of times Earth's field. These magnetic white dwarfs display spectral features split and shifted by the strong magnetism. The field origin remains debated. Magnetic fields might concentrate during stellar collapse. Binary mergers might amplify fields. Dynamo processes could generate magnetism in certain conditions. Whatever the origin, these magnetic white dwarfs appear more frequently in globular clusters than in the general stellar population. The dense environment might enhance formation mechanisms. Binary interactions could create conditions favoring magnetic field generation. The strong fields affect cooling rates and atmospheric structure. They make these white dwarfs appear different from normal cooling stellar cores. Magnetic white dwarfs represent another exotic product of stellar evolution in extreme environments. Dead stars carrying fossil magnetic fields from violent formation processes. Some binary stars orbit so close they spiral inward through gravitational radiation. They are destined to merge. Gravitational waves carry energy away from binary systems. This energy loss shrinks the orbit. The stars spiral closer together. Eventually they will merge in violent collisions. Scientists predict these clusters contain numerous such systems: white dwarf pairs, neutron star pairs, mixed pairs containing one white dwarf and one neutron star, all orbiting close enough that gravitational radiation dominates their evolution. Current gravitational wave detectors primarily detect mergers involving black holes or neutron stars from the general galaxy population. Future detectors will observe mergers from globular cluster sources. These events will reveal the population of tight binaries hiding in dense stellar environments. The merger timescales vary. Some systems merge quickly. Others take billions of years. The clusters contain binaries at all evolutionary stages, from widely separated to nearly touching. These systems represent future gravitational wave sources. Cosmic events waiting to occur when orbital decay finally brings the components into catastrophic contact. Gamma-ray telescopes revealed something remarkable. Entire globular clusters glow in high-energy radiation. The emission does not come from single sources. It is diffuse emission filling the cluster volume. The gamma rays originate from populations of millisecond pulsars collectively lighting up their host clusters. Each millisecond pulsar generates gamma rays through magnetospheric processes. Particles accelerate in strong magnetic fields. The accelerated particles produce gamma-ray photons through interaction with the fields. Individual pulsars are too faint to detect separately, but clusters contain dozens of millisecond pulsars. The combined emission becomes detectable. The gamma-ray glow reveals the pulsar population even when individual sources remain too weak to observe. The emission intensity correlates with cluster properties. Dense clusters show stronger gamma-ray emission because they harbor more millisecond pulsars. The gamma rays prove these ancient stellar cities contain large populations of recycled neutron stars spinning at absurd rates and illuminating their homes with high-energy radiation invisible to optical telescopes. How do you create hundreds of thousands of stars simultaneously in a single location? The early universe provided the conditions. These clusters formed when the cosmos was young. Gigantic gas clouds existed in the chaotic early universe. Densities reached levels far exceeding modern star-forming regions. Something triggered catastrophic collapse, perhaps colliding gas streams, perhaps density fluctuations from cosmic structure formation. The trigger remains debated. The outcome is clear. The entire cloud collapsed essentially at once. Star formation happened rapidly rather than gradually. Hundreds of thousands of stars ignited within a relatively short period. This burst mode creation produced populations with uniform ages and compositions. The formation process consumed most of the gas cloud. Little gas remained for extended later star formation. The cluster emerged as a bound gravitational system containing only stars. This rapid assembly in dense early universe environments explains why these clusters are both ancient and chemically uniform. They represent single burst star formation from early gas clouds. Newly formed clusters do not immediately resemble the structures we observe today. They undergo dramatic transformation in their first billion years. The initial cluster contained residual gas not converted into stars. Massive young stars produced intense stellar winds. These winds swept through the cluster, driving out remaining gas. Supernova explosions from the most massive stars injected additional energy. The combined effect expelled gas from the cluster's gravitational well. Within tens of millions of years, the cluster became gas-free. Without gas, only stars remained. They settled into gravitational equilibrium. The cluster established stable structure through stellar interactions. Relaxation processes began redistributing energy. This early phase determined the cluster's future evolution. Gas expulsion removed significant mass. The cluster expanded to accommodate reduced mass. Stars on the outskirts gained enough energy to escape. The survivors formed the gravitationally bound system that would persist for billions of years. Early evolution transformed chaotic gas-rich proto-clusters into stable, purely stellar systems. These clusters lose members continuously through a process invisible to casual observation. One star at a time escapes into the surrounding galaxy. Gravitational encounters constantly redistribute energy between cluster members. Some stars gain enough energy to exceed escape velocity. These energized stars depart permanently. The evaporation rate depends on cluster properties. Dense clusters lose stars more slowly because deeper gravitational wells hold members more tightly. Low-mass clusters evaporate faster because weaker gravity releases stars more easily. The process accelerates over time. Losing stars reduces total mass. Lower mass means weaker gravitational binding. Remaining members escape more easily. The cluster shrinks and mass loss accelerates. Evaporation particularly affects the lightest stars. Mass segregation concentrates them near the tidal radius where escape is easiest. Each departing star carries energy away from the cluster. This energy extraction speeds up internal evolution. Evaporation represents the steady bleeding away of cluster members, a glacial dissolution occurring star by star across billions of years. Some clusters experience sudden structural transformation after billions of years of gradual evolution. The core implodes catastrophically. Mass segregation concentrates heavy stars in the core. Density increases steadily. Encounter rates accelerate. Energy flows faster from core to envelope. The core contracts. Eventually, the contraction becomes unstable. The core enters runaway collapse. Density skyrockets while radius plummets. The collapse accelerates until something halts it. Binary star interactions often stop the collapse. Closed binaries absorb energy from passing stars. This energy injection heats the core and reverses contraction. The cluster stabilizes in a new configuration with extremely dense collapsed core. Not all clusters experience core collapse. Low-density clusters evolve too slowly. They might dissolve through tidal disruption before reaching collapse. High-density clusters often show collapsed cores. Tiny central regions with stellar densities exceeding anything in the outer cluster. Core collapse represents gravitational instability's ultimate expression. The heart of a stellar system implodes when energy extraction can no longer be sustained. Clusters do not orbit in isolation. They pass through different galactic environments experiencing varying gravitational stresses. When a cluster passes near the galactic center, tidal forces intensify dramatically. The galactic gravitational field pulls harder on the cluster's near side than its far side. This differential force stretches the cluster violently. The stretching can exceed the cluster's internal binding. Outer stars feel tidal forces stronger than the cluster's gravity. They tear away in large numbers during the passage. Scientists call these events tidal shocks. Basically, sudden violent mass loss episodes caused by strong external gravity. Each shock strips away a fraction of the cluster's population. The lost stars disperse into the galactic halo. Clusters on eccentric orbits experience repeated shocks. Each closed passage removes more members. The cumulative effect can destroy entire clusters over billions of years. Tidal shocks represent the most violent mechanism for cluster dissolution. Sudden catastrophic stripping during encounters with overwhelming galactic gravity. Globular clusters orbit through three-dimensional halos surrounding galaxies. Some orbits intersect the galactic disk where stars and gas concentrate. Each disk passage subjects the cluster to a rapid change in gravitational force. The cluster passes through the dense disk potential. Stars in different parts of the cluster respond differently to that changing pull. These interactions inject energy into the cluster. Some stars are pushed onto wider orbits. Others gain enough energy to escape more easily later. The process is called disk shocking, basically an impulsive tidal disturbance during passage through the disk. It is distinct from dynamical friction. Disk shocking does not mainly reduce the cluster's orbital energy. It heats the cluster internally and can help loosen stars. Repeated disk passages therefore contribute to long-term cluster destruction. They weaken the cluster and make later stripping easier. Disk passages demonstrate how even diffuse galactic structure can affect cluster evolution through cumulative gravitational interactions. Most clusters evolve in isolation. Occasionally, two clusters collide and merge in spectacular events. Cluster collisions happen when orbital paths intersect. The probability is low because clusters occupy small volumes in large galactic halos. But over billions of years, some encounters occur. When clusters collide, they do not bounce apart. Gravitational binding can exceed collision speeds. The clusters merge into a single larger system. The merger violently reshapes both clusters. Tidal forces stretch them. Stars mix together. The combined system eventually relaxes into a new equilibrium configuration. Evidence for past mergers appears in some clusters. Unusual velocity distributions might indicate recent collisions. Elongated shapes could reveal ongoing mergers caught in progress. These rare events demonstrate that cluster evolution sometimes proceeds through dramatic collisions rather than gradual processes. Mergers represent cosmic accidents that occasionally transform cluster populations. Dying clusters leave visible traces. Long stellar streams stretch across space, tracing the cluster's orbital path. When stars escape through tidal stripping, they do not disperse randomly. They follow orbits similar to the cluster's orbit. Escaped stars spread along the orbital path, forming extended tails. These tidal tails contain stars stripped during multiple orbital passages. Leading and trailing tails extend from both sides of the cluster. Some tails stretch across thousands of light years. Telescopes have mapped numerous tidal tails around globular clusters. The tails prove tidal stripping is actively destroying these systems. They trace the cluster's orbits through space. Tidal tail properties reveal destruction history. Longer tails indicate more advanced destruction. Multiple tail structures might indicate complex orbital histories. These stellar streams represent the ghosts of cluster populations. Stars that once orbited together now spread along the path their former home follows through the galaxy. Some cluster cores might harbor invisible massive objects. The evidence comes from stellar motions near cluster centers. Stars close to the core should move predictably based on visible stellar mass. Measurements sometimes reveal faster motions than expected. The excess velocity suggests hidden mass concentrating in the core. One explanation involves intermediate mass black holes, objects weighing thousands of solar masses. These hypothetical black holes would fall between stellar black holes and the supermassive monsters in galaxy centers. Formation mechanisms remain uncertain. Perhaps stellar collisions built massive stars that collapsed into black holes. Perhaps multiple stellar black holes merged over billions of years. The process would require extreme densities and long timescales. Not all clusters show evidence for central black holes. The signals remain ambiguous in many cases. But if confirmed, These hidden monsters would profoundly affect cluster evolution. They would dominate central dynamics and alter long-term fate. Central black holes represent one of globular cluster astronomy's major unsolved questions. Invisible objects that might control the destinies of stellar cities. These ancient structures survived billions of years, but survival cannot continue indefinitely. Two processes guarantee eventual destruction. Evaporation removes stars gradually. Tidal stripping tears away members during galactic passages. Both continue relentlessly. The timeline depends on initial mass and orbital properties. Small clusters on tight orbits dissolve quickly. Massive clusters on distant orbits survive much longer. Eventually, every cluster reaches a critical threshold. Remaining mass drops too low to maintain gravitational binding. The structure dissolves completely. Stars disperse into the galactic halo. Some stars might fall into the galactic center. Others might escape into intergalactic space. The cluster as a coherent structure ceases to exist. Only individual stars remain as testimony to the ancient stellar city. Final dissolution represents the endpoint of billions of years of evolution. It is the complete erasure of structures that formed when the universe was young. Not all clusters face identical fates. Initial mass determines survival likelihood. Massive clusters resist destruction better than lightweight ones. Greater mass means deeper gravitational wells. Deeper wells hold stars more tightly against evaporation and tidal stripping. Observations confirm this relationship. The most massive clusters show minimal signs of disruption. Less massive clusters display advanced tidal damage. The smallest clusters have already disappeared. Orbital properties also matter. Clusters on distant orbits experience weaker tidal forces. They survive longer than clusters on tight orbits, passing frequently near the galactic center. The combination of mass and orbit determines lifespan. Massive clusters on distant orbits might survive beyond the current age of the universe. Small clusters on close orbits dissolve in billions of years. This mass-dependent survival explains why we observe a range of disruption states. From pristine massive clusters to fragmenting remnants barely holding together. Initial conditions determined which clusters would witness the universe's entire history, and which would vanish along the way. Measure iron content in different globular clusters. The values scatter across a wide range. This scatter tells the story of how our galaxy chemically evolved. Some clusters contain iron levels barely reaching 1% of the Sun's value. Others show several percent. The range spans more than a factor of 10. The variation reflects formation timing. Lower metallicity clusters formed first from nearly pristine gas. Higher metallicity clusters formed later after multiple stellar generations had enriched the surrounding gas with heavy elements. Scientists use the term metallicity spread, basically the range of iron content across the cluster population. This spread maps the galaxy's chemical enrichment history. Each cluster preserves the metallicity of its formation environment. The distribution isn't random, it shows distinct patterns. Metal-poor clusters outnumber metal-rich ones. The distribution peaks at very low metallicity with an extended tail toward higher values. This pattern reveals how chemical enrichment proceeded in the early galaxy. Rapid initial formation from primitive gas, followed by slower enrichment, creating progressively more metal-rich clusters. Not all globular clusters formed simultaneously. Age measurements reveal multiple formation episodes, separated by billions of years. The oldest clusters date to the universe's first billion years. These ancient populations represent the galaxy's initial star formation burst. Slightly younger clusters show formation ages several billion years later. This age spread indicates episodic formation. The galaxy didn't assemble smoothly. It grew through discrete events, perhaps mergers with satellite galaxies. Each merger triggered new cluster formation. The age distribution correlates with metallicity. Older clusters tend toward lower metallicity. Younger clusters show higher metal content. This age-metallicity relation confirms that chemical enrichment proceeded as the galaxy aged. Multiple cluster generations preserve the galaxy's assembly timeline. They mark when major formation events occurred. The age distribution demonstrates that our galaxy didn't form in one event, but assembled gradually through multiple episodes across billions of years. Track globular cluster orbits through the galaxy. The orbital shapes reveal the galaxy's formation history. Some clusters follow nearly circular paths around the galactic center. Others travel on highly elongated elliptical orbits. Still others show orbits tilted at steep angles to the galactic disk. These orbital properties aren't random. They reflect formation environments. Clusters born in the main galaxy tend towards circular orbits aligned with galactic rotation. Clusters captured from satellite galaxies often show eccentric tilted orbits. Scientists measure orbital eccentricity, basically how elongated an orbit is compared to a perfect circle. High eccentricity indicates capture origin. Low eccentricity suggests in situ formation. The orbital distribution splits into distinct families. One group shows low eccentricity orbits, consistent with formation in the main galactic halo. Another shows high eccentricity orbits indicating capture from merging satellites. These orbital families preserve evidence of ancient galaxy mergers invisible through any other observation. Plot globular cluster metallicity against population numbers. The distribution shows two separate peaks rather than one smooth curve. One population clusters around very low metallicity. Another concentrates at moderately higher values. The gap between them creates what scientists call bimodality, basically a distribution with two distinct peaks. This split indicates two different formation channels. The metal-poor population likely formed in the main galactic halo during early collapse. The metal-rich population probably formed in the galactic disk or bulge slightly later. The two populations also differ in spatial distribution. Metal-poor clusters show spherical distribution throughout the halo. Metal-rich clusters concentrate more toward the galactic center and disk. Metallicity bimodality reveals that our galaxy formed through at least two distinct processes. The halo assembled first from metal-poor gas. The disk and bulge formed later from gas already enriched by previous stellar generations. These two cluster populations mark fundamentally different formation environments and timescales. The horizontal branch shows different color patterns in different clusters. These variations reveal subtle differences in initial helium content. Some clusters display predominantly blue horizontal branches. Stars cluster toward the hot blue region of the diagram. Other clusters show redder distributions. The color spread indicates helium abundance variations. Higher helium content drives stars toward the blue end. Lower helium pushes them redward. Measuring horizontal branch colors therefore constrains initial helium abundance. The helium variations are small but significant. They indicate that even the first stellar generations didn't form from perfectly identical gas. Slight composition differences existed in the early universe. These abundance variations reflect conditions during primordial nucleosynthesis. Basically the nuclear reactions that occurred in the first minutes after the Big Bang. Different regions experienced slightly different conditions. The resulting helium abundance variations persisted and appear today in horizontal branch morphology. These subtle differences preserve records of cosmic conditions from the universe's earliest moments. Map where globular clusters orbit around the galaxy. They don't concentrate in the galactic disk. They surround the galaxy in a roughly spherical distribution. The spatial pattern extends far beyond the visible galactic disk. Clusters populate a three-dimensional halo. This halo shows approximate spherical symmetry around the galactic center. The distribution constrains the galaxy's early structure. The halo must have formed before the disk. Material settled into the disk later, while clusters remained in their original spherical distribution. The outer halo clusters reach enormous distances. Some orbit hundreds of thousands of light-years from the galactic center. They trace the galaxy's gravitational influence to its limits. This spherical distribution proves the galaxy initially had spherical structure. The disk formed later through gas settling to the equatorial plane. Globular clusters preserved their original halo orbits. Their spatial arrangement maps the galaxy's primordial architecture before disk formation flattened the structure. Measure how fast globular clusters orbit the galaxy. The velocities reveal the galaxy's total mass, including invisible components. Cluster orbital speeds depend on the gravitational field. Stronger gravity requires faster orbital velocities. Measuring velocities throughout the halo maps the mass distribution. The velocities stay surprisingly high even at large distances. This indicates substantial mass beyond the visible stars. Scientists call this the velocity dispersion profile, basically how orbital speeds vary with distance from the galactic center. The high velocities prove dark matter dominates the galaxy's mass. Visible matter alone can't produce the observed speeds. A massive dark matter halo must surround the galaxy. Globular cluster kinematics provide some of the best evidence for dark matter. The velocities measure the gravitational field directly. The measurements confirm that our galaxy contains far more mass than we can see. These ancient clusters serve as test particles, revealing the invisible dark matter halo enveloping the galaxy. Our galaxy isn't unique. Other galaxies also host globular cluster systems. Comparing different galaxies reveals universal formation patterns. Giant elliptical galaxies contain thousands of clusters. Dwarf galaxies host just a few. The total number scales with galaxy mass. This relationship holds across galaxies spanning enormous mass ranges. The metallicity distributions show similar bimodal patterns in many galaxies. Two cluster populations appear consistently. This suggests similar formation mechanisms operated in different galaxies. Cluster systems also trace galaxy assembly. Galaxies that merged with satellites show disrupted cluster distributions. Undisturbed galaxies display regular patterns. Studying extragalactic cluster systems reveals that globular cluster formation follows universal laws. The same processes that created our galaxy's clusters operated throughout the universe. These observations demonstrate that galaxy evolution proceeds through similar mechanisms regardless of environment. Globular clusters serve as universal markers of galaxy formation. Not all our galaxy's globular clusters formed here. Some originated in smaller galaxies later consumed through mergers. Scientists identify accreted clusters through chemistry and kinematics. These clusters show peculiar element ratios or unusual orbital properties. They don't match the patterns expected for native formation. Some accreted clusters group into streams. These streams mark destroyed satellite galaxies. When a satellite galaxy merges with our galaxy, it tears apart. But its globular clusters survive and spread along the merger orbit. The Sagittarius dwarf galaxy is currently merging with our galaxy. Several globular clusters appear associated with this merger. They trace the dwarf galaxy's dissolution path through space. Accreted clusters preserve evidence of ancient galaxy cannibalism. Our galaxy consumed multiple smaller galaxies throughout its history. These mergers contributed their cluster systems to our current population. The accreted clusters testify that galaxy growth proceeded partly through devouring smaller neighbors. Cosmic cannibalism recorded in the orbits and chemistry of surviving cluster populations. Current technology approaches limits for studying globular clusters. Next-generation instruments will revolutionize our understanding. The Gaia satellite measures stellar positions and velocities with unprecedented precision. It maps cluster members and determines orbits accurately. Future data releases will provide complete census of cluster populations. Next-generation telescopes will resolve individual stars in clusters throughout the local galaxy group. This extends detailed studies beyond our immediate galaxy. Comparison across multiple galaxies becomes possible. Spectroscopic surveys will measure chemical abundances for millions of cluster stars. These data reveal subtle abundance patterns invisible in current observations. They constrain formation processes with far greater precision. Gravitational wave detectors will observe binary mergers originating in globular clusters. These observations test predictions about exotic compact object populations. They reveal processes invisible through electromagnetic radiation. These future observations will answer long-standing questions about cluster formation, evolution, and fate. They will connect cluster properties to cosmological models. Advanced research will transform globular clusters from astronomical curiosities into precision tools for understanding galaxy formation and cosmic evolution.